Towards the end of the previous video, we saw how you can get proportionality using both the triangle proportionality theorem and from similarity. The following question is going to help us to practice these skills yet again, right? So it says that in the diagram below, BC is equals to 17 units, right? And very important, BC is the diameter of the circle, right? The length of the chord BD is 8 units, and the tangent at B meets CD produced at A. Okay, so already you need to start integrating all the knowledge that you've accumulated. When we talk about things like the diameter and the tangent, you need to go back into Euclidean geometry, specifically your circle geometry theorem, so that you know that the tangent is always perpendicular to the radius or slash diameter at that point of contact, right? So we have a 90-degree angle there at B. Another thing is that when you have a diameter that subtends an angle at the circle, right, that angle is also 90 degrees, and we call this an angle in a semicircle, right? And then very nicely we need to now point out our theorem that we are busy working with, okay? Over here in triangle BDC, okay, we have that EF is parallel to BD, giving us a line drawn parallel to one side of the triangle. Okay, so now you've analyzed your diagram, you should be able to answer your questions. Question 10.1 says, calculate with reasons the length of DC, right? So DC is part of this triangle that I told you about. So in triangle BDC, right, you can see I've already noted the fact that I have a 90-degree angle over there, so we don't have to be fancy about this. We can calculate DC using Pythagoras. Okay, so the first thing we need to note, because this was not given, we have to tell them that angle BDC is equals to 90 degrees, and this is an angle in a semicircle. Right, so that's the first thing we need to tell them. And because we have an angle in the semicircle, we're going to apply Pythagoras theorem. So DC squared is going to be equals to BC squared minus BD squared. Okay, and this is by Pythagoras. Right? So this is given to us as 17, this is 8. Then if you plug all of this into your calculator, you can work out that DC is equals to 15 units. Okay, moving on. Question 10.2.1. Right, let's first read over here. E is a point on BC, such that BE to EC is equals to 3:1. Right. So they're giving us the ratio of BE to EC. So given BE to EC is in the ratio 3:1, right? Whenever I have 1 in my ratio, I really like it, because that means that I can say that therefore BE is equals to 3 times EC. And this will come in handy quite soon, you'll see, right? Okay. They tell us that EF is parallel to BD with F1 DC. We've already seen that. Okay. Now they say calculate with reasons the length of CF. Okay. So CF is this length over here. Notice I've landed on a parallel line. So this means that this is a great opportunity to apply the proportionality theorem. Okay. So if I take the proportion CF to DC, right, CD, this should be the same as the proportion of EC to BC. Okay, so Notice I created exactly the same shape on both sides. Let's just clean our diagram. Keep it clean, right? So you can compute this one of two ways. You can use ratios or you can use links. If you decide to use ratios, make sure that you use ratios throughout. Okay. I'm going to use links. Okay. So we need to give a reason for this first. This is a line parallel to one side of a triangle. Okay. So as noted, I said I'm going to use links. Okay. So I'm first going to compute EC because that's the only link that I don't have. I notice that BC is equals to BE plus EC. Okay. Now I'm going to use what I derived above over here. So BC is equals to BE is 3 times EC. Okay. Plus EC. Alright. So BE is equals to 4 times EC. So then, therefore, EC is equals to 17 over 4 units. Okay. Now I can go over to calculating CF, right? So just rearranging this by multiplying both sides by CD, you have CF is equals to EC over BC. Okay. So EC in terms, times CD. So EC in terms of a length is 17 over 4. This is divided by BC, which is 17, multiplied by CD, which is basically DC. This we calculated above as 15. Right. You can then plug all of this into your calculator. This will give you that CF is equals to 3,75 units. Okay, so this is how you would have calculated CF using links. Okay, so if you had decided to use ratios, you need to stick with using ratios, and this, I'm going to show you what that looks like now. Okay, so EC, right? So notice EC is given here as BE to EC is given as 3:1. Okay, so remember right in the first video I taught you how to use placeholders. So you would go into your diagram and you would say BE is 3x and EC is x. Okay, this x is our placeholder so that we don't confuse this with links that are given. Okay, so now you want the ratio EC to BC. So in terms of ratios, that will be x by x plus 3x is 4x. Okay, the x's will cancel out. That is why using a placeholder doesn't really change anything. And then multiplied by CD, this is 15. Okay, so don't get confused. When you use ratios, basically how you need to think about it is kind of like percentages. Okay, you're saying that CF is 1/4 of DC. Okay, and that's how you're basically computing it. And if you plug this into your calculator, you should get exactly the same answer of CF is equals to 3,75 units. Okay, so question 10.2.2 then is asking us to prove that the triangle BAC, so this big triangle, I'm not going to highlight it, remember that's the big triangle, is similar to triangle FEC. So FEC, so this little tiny triangle here, let's just remove this highlight. Okay, so now we're working in the small little triangle to the big triangle. Alright, small triangle, big triangle. Okay, remember in the previous video I already told you that a little cheat is that when you see similarity, you need to know already that the placement of these letters is as per equal angles, right? So you can now use the placement of these letters to go searching and find the reason why the angles are equal, and that's going to help you write out a proof as to for similarity. Okay, so we're going to say in triangle BAC and triangle FEC. Okay, so BAC, FEC, the first thing we can see is that angle C is common, right? The next thing we see over here is that they're saying that angle B is equals to angle F, right? So if we go along this triangle, the small one, there's angle F, right? And the big triangle, there's angle B, right? Okay, so angle B is 90 degrees. Would that be equal to angle F? Yes, because angle F is a corresponding angle to angle D over here, right? So this is 90 degrees as well, and thus they are equal. We're just going to have to prove it first before we state it. So we just need to repeat angle BDC is equals to 90 degrees, right? And this was proven above. Okay, so this is 90 degrees. Okay, and angle EFC is equals to angle BDC is equals to 90 degrees because these two are corresponding angles. EF is parallel to BD. Okay, then the reason why angle B over here is equals to 90 degrees is because the tangent is perpendicular to the diameter. So angle ABC is equals to 90 degrees because the tangent is perpendicular to the diameter, right? So angle F is 90 degrees and angle B is 90 degrees. So therefore angle FC is equals to angle ABC, right? So as our second point for similarity, just notice we're starting with the big triangle, so I'm going to say angle ABC is equals to angle EFC, right? I'm going to say here, proven above, right? And then therefore we've proved two angles equal in these two triangles. The third angle will be equal because it's the third angle of the triangle. Therefore these two triangles are equiangular and thus similar. So triangle BAC is similar to triangle FEC. Okay, now just make sure again B is equals to F, because that's proven. A is equals to E, that will be the third angle, and C is equals to C, that's the common angle between these two triangles, right? So question 10.2.3 says calculate the length of AC, right? So AC is this length for in this big triangle ABC, okay? Because we've just proved similarity, chances are we're going to have to calculate this length from similarity, right? So let's go. AC is what we're looking for. So AC, meaning that we need to take the last two sides on the small triangle. AC will be to EC. Okay, this is equals to, let's take BC in the big triangle because we know what BC is equals to. So BC will be to FC. And the reason for this proportionality is similarity. So triangle ABC is similar to triangle FEC. Okay, now let's see if this is going to work out. EC, do we know that? Yes, we do. We calculated it before. BC, we do know. FC is over here. FC is exactly the same as CF. So yes, we calculated that in the previous question. We have all of these in terms of length, so we're just going to substitute, nothing difficult. Therefore, AC is equals to BC over FC times EC. Right? Remember, this is 17. We calculated this as 3,75, and this was 17 over 4. Okay. And then plugging this into our calculator gives us 19 to 2 decimal places, 27 units. Okay. Now, lastly, they say write down, given reasons, the radius of the circle passing through the points A, B, and C. Okay, so if you had a circle passing through A, B, and C, what would be the radius of that circle, right? Okay, notice something. Angle B is 90 degrees. So the same thing as this diameter BC subtending a 90-degree angle with the circle. If there was a circle passing through here, then this would be subtended by this line AC, making AC the diameter, right? And we just calculated the length of AC, so half of AC will be our radius, okay? So question 10.2.4, we can say that angle ABC is equals to 90 degrees, right? And we prove this above. Remember, we said it's because the tangent is perpendicular to the diameter, right? So therefore, this makes the chord, or the, well, if there was a circle through these 3 points, then this would be a chord, so it makes AC a diameter, right? And the reason for this is the inverse of the angle in the semicircle theorem. So you say that this chord subtends 90-degree angle, right? So because it subtends a 90-degree angle, it becomes a diameter. Therefore, our radius is going to be equals to AC over 2, which is 19,27 over 2, which works out to 9,63 units. Okay.